Hello student, welcome back to my channel Kunal sir at JEE NEET Chemist World. Today's topic discussions was JEE Advanced problem, as we are discussing last couple of video on those things, and today also I am going to discuss JEE Advanced problem on very important chapter, which is nothing but a states of matter. And in states of matter there is a real gas compressibility factor. Over there I am discussing that JEE Advanced problem, which is very important model for upcoming JEE Advanced 2025. Now, like last couple of JEE Advanced video, this will open up your new avenue. As far as states of matter is concerned, this is a part of a physical chemistry first year topic, and every year or alternate year there will be minimum physical questions. Out of 18 questions, around 6 to 8 questions come from physical, and sometimes 9 questions used to come from 9 to 10 questions from organic, but major part will be there organic and physical. So now in this physical, states of matter is one of the important chapter, though it is deleted from the JEE mains, but still it is there in JEE Advanced. That's why it's a very important topic of discussions. Directly come into the topic of discussions. Here if you look at the problem, they are giving the graph of compressibility factor Z versus P for 1 mole of real gas is shown in the following diagram. This is the diagram. And the graph plotted at a constant temperature. Temperature is 273 Kelvin. If slope of the graph at high pressure is 1 by 10 atmosphere inverse, the volume of one molecule of real gas in centimeter cube or cc means cubic centimeter is, they are giving 4 options. First options 9.3 into 10 power of minus 23. Second option 3.7 into 10 power of minus 20. Third options 9.3 into 10 power of minus 22. Fourth options 5.6 into 10 power of minus 20. To solve this problem, first we need to know few basic idea regarding real gas and compressibility factor, and that I am going to discuss first, then we will come to the problem. So now if you look at in the next slide, if you look at first for the real gas, for 1 mole of real gas, the equations will be equals to, for 1 mole of real gas equation will be equals to P plus A by V square into V minus B equals to RT. If it is a N mole, then N square A by V square V minus NB equals to nRT. But here I took it 1 mole, that's why all places N equals to 1. So that's why it is coming P plus A by V square into V minus B equals to RT. N mole, N square A by V square. Instead of B, NB, instead of RT, nRT. That is the idea. Now, whenever that means ideal gas equation equals to PV equals to nRT for N mole of ideal gas, and all pressure temperature, if any gas is following this PV equals to nRT, that is a ideal gas. But in reality there is no ideal gas. In a certain temperature and pressure they are behave ideally, which is nothing but a boil temperatures. And now this ideal gas equation, if you observe carefully, their pressure is there, volume is there, number of moles is there, and temperature is there. So PV equals to nRT. But now whereas real gas, not only P and V term is there and RT is there, but also additionally with pressure something additional part is there, and from volume something subtracted part is there. So now if you look at, that means whenever there is a pressure correction is there in ideal gas, from ideal gas situation to the real gas, and there is a volume correction is there from ideal gas situation to the real gas situation, then only that will be equals to the RT. This is another part of discussion. Why pressure correction is there? Briefly I am telling, because in case of ideal gas we used to consider there is a no force of attractions and repulsion between the gas molecule, and gas molecule volume, if we consider the volume of the container is the volume of the gas molecule. This is ideal gas situation as per the kinetic theory of the gases. Now, but in reality, there what is going to happen? In reality, whenever the pressure is very, very high and the volume is very, very low, then there will be a repulsion between the molecule will be a dominant factor, and that time the volume of the gas molecule is not the volume of container. Even in ideal gas situation, they used to discuss the volume of one gas molecule in insignificant with respect to the volume of the container. But when this situation is arises a very, very extremely high pressure situation, then volume of each molecule is significant, and as well as that gas molecule used to consider as a hard sphere. So that's why the some part of the container which will be excluded volume, where the gas molecule can't travel, and that part we need to discuss what is the excluded volume, and that will come into the real gas situation. So as there is a force of attraction is there and repulsion is there, naturally there will be a pressure correction, naturally there will be a volume correction. That's why V is the volume of container. From there something need to be subtracted. With pressure something need to be added. Why? Because there is a force of attraction is there. So that's why what is the excluded volume we are going to discuss. So if you think about binary collisions of gas molecule, binary collisions of gas molecules, then what will be the situations? The two gas molecule can't penetrate to each other, they just can touch to each other. This is the two gas molecule. If you look at, this is the radius of one molecule R, another molecule radius also from here R. Now if you look at this, the area what I am drawing, you look at very carefully. This area, if you look at, that means this part, if you look at this part, this distance is nothing but what? This is a 2R. This 2R of the volume is a incompressible volume, or it is called as a excluded volume. So now, or if you look at that excluded volume, so then what is the excluded volume? Then excluded volume will be equals to excluded volume per pair of molecules will be equals to 4/3 pi r cube. You know the volume of the sphere, but here r equals to how much? 2r. So then excluded volume per pair of molecule 4/3 pi r cube, that means 2r whole cube. So this is the excluded volume per pair of molecules. Now if you look at the situation, if I want to do excluded volume per molecule, excluded volume per molecule, that will be equals to 1/2 into 4/3 pi 2r whole cube, which is nothing but a 1/2 into, if you look at over here, 2 cube means 8 and into 4/3 pi r cube. So then 2 into 4, which is coming nothing but a 4 into 4/3 pi r cube. 4 into 4/3 pi r cube. 4/3 pi r cube. R is the radius of the gas molecule. So that's why, that means it is nothing but a excluded volume per molecule. Excluded volume per molecule will be equals to 4 into volume of one molecule. Yes or no? Now if you look at volume of one molecule, now if you look at B is nothing but represent repulsive factor as well as excluded volume of real gas per mole. This B is nothing but a excluded volume of real gas per mole. That's why if 1 mole it's a 1B, if it is a n mole it is a nB. Now here the excluded volume Per molecule we got it this one. That's why B will be equals to, I can write down 4 into volume of one molecule, volume of one molecule, one molecule, one molecule into Avogadro number. Avogadro number means what? 1 mole of molecule, 1 mole of molecule. So that's why B generally used to express per mole, and already you know very well 1 mole equals to how much? Avogadro number of Na is a Avogadro number. That's why B equals to 4 into volume of one molecule into Avogadro number. This concept we will utilize to solve this problem. Excluded volume I explained very clearly, as well as I correlate B equals to 4 into volume of one molecule into Na. How it is coming? That part also I explained. So now, next, if you look at the problem what they are giving, previous slide you look at. In the previous slide, that problem they discussed, and they give a one plot, and in that plot what they are giving, you look at Z. Z is a compressibility factor versus P plot they are giving, and the high pressure region slope they are giving, slope is 1 by 10. And now if you, this is a very basic mathematics, if you have a y-axis plot is there, y versus x-axis plot is there, then your slope will be equals to, everybody knows, dy by dx. dy by dx equals to your slope. Same thing we will apply over there. Now before going to that, we will do the compressibility factor. What is the compressibility factor? That compressibility factor is Z. Z will be equals to PV by RT for 1 mole of, expression wise, for 1 mole of gas. Compressibility factor Z equals to PV by RT for 1 mole of gas. If it is n mole, so then what we will do? So then immediately we can do like that, PV by nRT. So that's why here 1 mole we took. So that's why Z equals to PV by RT. And that Z plotted against the pressure. So now initially what is happen? Whenever the pressure is increases, then volume is start decreasing, and when volume is coming some optimum positions, then there will be a force of attraction between the gas molecule. And now after certain point, when volume will be more close to each other, volume will be more or less, then repulsive force will be a dominant factor, and naturally Z will start increases. How? Let us look at the explanations. Then how the Z will be increases when the pressure is extremely high, then we will come to the problem discussions. Z equals to, we know very well, Z equals to, we know, PV by RT. Now you understood this funda. Whenever pressure is very, very high, volume will be what? Very, very low. When the volume will be very, very low, then my repulsive force will be dominant. Then repulsive force whenever will be dominant, then what is going to happen? Your repulsive force is a dominant factor. Then immediately once repulsion will start, the molecule will go away to each other. Then volume will start increasing. And then immediately my PV part, this part will be increasing, and definitely my Z will be what? Increases. That's why in the graph also is showing Z, high pressure Z is start what? Increasing. Now let us look at the van der Waals gas equation. For 1 mole we know P plus A by V square. This real gas equation is nothing but a van der Waals gas equation. P plus A by V square, V minus B equals to RT. This is a real gas equation. Specifically we call it as a real gas equation, specifically we call it as a van der Waals gas equations, because famous scientist van der Waals discovered this idea. So van der Waals gas equations. Now if you look at when the high pressure region, at high pressure what is happening? Repulsive force is a dominant. Repulsive force dominant. Then attractive force we can neglect. This part is representing, especially A is nothing but a attractive force. attractive force, and this part B is representing excluded volume as well as repulsive force factor. This is a repulsive force part. So now if you look at this, at high pressure repulsive force is a dominant, then neglecting repulsive force part, neglecting repulsive attractive force part, neglecting attractive force part. Why we are neglecting attractive force? Because repulsive force is a dominant factor in the high pressure region. At high pressure region repulsive force is a dominant, that's why neglecting attractive force. Then after that, if you write down the van der Waals equations for 1 mole of gases, what is coming? P into V minus B equals to RT, and then immediately PV minus PV equals to RT. Now PV will be equals to your RT plus PB, and then divided by RT both side, divided by RT both side. Then what you will get over here? Then you will get PV by RT equals to 1 plus PB by RT. And now PV by RT equals to, you know, this is nothing but your Z. Z equals to 1 plus PB by RT. 1 plus something. Generally for the ideal gas, Z equals to 1, and high pressure region Z is greater than 1. So that's why Z equals to high pressure region 1 plus something. So obviously Z will be what? Greater than 1. That's why whenever Z is greater than 1, it is the repulsive force is a dominant factor. So whenever repulsive force is dominant factor, you need to apply more and more. Your compressibility factor is greater than 1. That means the gas is very hard to compress. So that is the, because also you know physical significance, their repulsive part is a dominant. When the repulsive force is a dominant, the gas molecule don't want to come very close to each other. So that's why gas is very hard to compress. And also by logic we prove high pressure region Z is greater than 1 and Z equals to 1 plus PB by RT. Now these things we will capitalize. Look at into the next slide for solving the problems. If you look at, then we got it high pressure. At high pressure, what we got, my dear student? At high pressure, Z equals to 1 plus PB by RT. Now, what is slope? Just now I explained Z versus P they give you. Then what will be? Z versus P plot is there in the problem. In Z versus P plot, slope will be equals to, you know, y versus x plus dy by dx is a slope. So then Z versus P plot, your slope will be dz by dp. Yes or no? So now dz by dp will be your slope. Then again that's why differentiating with respect to P. Differentiating with respect to P. Then what you will get over here? dz by dp equals to a constant term differentiations will be equals to 0, and here B by RT is a constant term. ddp of P equals to 1. So that's why you will get dz by dp equals to what? B by RT. We are getting these things. And also in the problem they told dz by dp. In problem they are giving, that is nothing but, this is nothing but your slope, and this problem slope equals to, they are giving, in problem they are giving this equals to 1 by 10 atmosphere inverse. So then immediately what I can write down? B by RT equals to 1 by 10. And then immediately B equals to, what I can write down? B equals to RT by 10. Again we know B equals to 4 into volume of one molecule. Volume of one molecule into Avogadro number equals to RT by 10. So now in the question they are asking volume of one molecule. Then you look at, from here I am writing over here. Then volume of one molecule will be equals to volume of one molecule. Volume of one molecule will be equals to So RT by below there will be 4, it will come 4. If you look at B equals to, we write down 4 into volume of one molecule into Avogadro numbers. So then immediately volume of one molecule, if you calculate that, volume of one molecule will be equals to RT by 10 into 4Na. So then immediately what I can write down, RT by 4 into Na into 10. We are getting volume of one molecule. Now R equals to in liter atmosphere, if you put R equals to, it will come 0.082. So R value is 0.082 liter atmosphere. So then immediately instead of these I can utilize 1 by 12 or I can utilize 22.4 by 273. These things are these things. Then immediately instead of R I am putting 22.4 by 273, and temperature is also is there 273, and these things by this one, so obviously these will come over here. 4 into Avogadro number 6 into 10 power of 23 into 10 is over here. So then immediately you look at 273 cancel out. Then immediately what you will get, this 10 I divided by 22.44, which will come 2.24 divided by over here you have a 4, and here you have a into 6 into 10 power of 23. So 1 by 4 equals to 0.25, and here these things, if you look at these things is your calculations. You can do your calculations over here itself. So you have a 2.24 divided by 4 into 6 into 10 power of 23. So now if you go for these entire calculations and simplifications, I hope your answer used to come in the range of 9.3 in the form into 10 power of minus 22 it will come, but it is there in liter. You have to convert into the milliliter or cc, that's why multiplied by 10 power of 3, because this is I took it liter. So 22.4 liter by 273, that is nothing but this liter atmosphere. So now this liter I need to convert into the ml. Ml means centimeter cube or cc, that's why I want to multiply by 10 power of 3. So then after that, this is your final calculation, this part. If you do final calculations this part, then final reagent used to come 9.3 into 10 power of minus 22 cc. This is coming, the volume of one molecule is 9.3 into 10 power of 22 cc. And now you look at into your options. Into the first slide, the options was there. If you look at that options into the first slide, then you will get what is the option is there into the first slide. So then only we can opt the answers into the first slide. We will get our answer for the above problem which are giving into the JEE Advanced model problem. If you look at 9.3 into, they are asking the volume of one molecule of real gas in centimeter cube or cc, which is nothing but a 9.3 into 10 power of minus 22. That option is there. That's why which options will be your answer? Third options will be your answer. I hope it is clear to everybody. What I did, I am doing the briefing again. First, we write down the how to do a excluded volume B for 1 mole of per mole of real gas, which is nothing but a 4 into volume of one molecule into Avogadro number. That part also I explained very clearly. Then I took a van der Waals gas equation for 1 mole, and for I apply high pressure region, what will be the van der Waals gas equation, that I derive over there by neglecting the attractive force. And then we got the Z equals to expressions 1 plus Pb by RT, and Z is greater than 1 at high pressure region and gas is very hard to compress. And then I do differentiating with respect to P, dz by dP, and then I got the term B by RT. And then they are telling, and dz by dP is a slope. From this graph we can observe, because y versus x plot, dy dx is a slope, z versus p plot, dz by dp is a slope, and that slope they are telling 1 by 10. Obviously b by rt equals to 1 by 10. We equate that one. B equals to, I put 4 into volume of one molecule into Avogadro number. Then R, I took it liter atmosphere. Instead of 0.082, I put 22.4 liter by 273, so that temperature constant 273 both can be cancelled. And then after that liter I need to convert into the ml or centimeter cube, because the final answer they are asking in terms of a cc or centimeter cube. That's why I multiplied by 10 power of 3, and final calculations if you do, it used to come 9.3 into 10 power of minus 22 ml, or which is nothing but a centimeter cube or cc. That's why, which option is your answer? Third option is your answer. I hope everybody got the clarity how to approach these states of matter problems, especially these van der Waals equations type problem for upcoming JEE Advanced. To get more and more this type of video, please have a watch my channel, come into my channel and subscribe and give a comment, so that you can get your customized problem, customized clarity about the concept, and you can succeed for your upcoming exam. Thank you very much. Thank you all for watching this video. Thank you, my dear student.